In this video, I'm going to show you how to fit an equation to data, doing essentially a regression. Now, in order to do this, we're going to want to use SciPy's minimize capabilities. So we're going to first import NumPy. In this case, just in case. And then from scipy.optimize, we're going to import minimize. Minimize. There we go. Let's make sure those two imports work. Excellent. Okay, so to save some time, I have some example data that I want to use to fit on. Let's go ahead and generate this data. So it looks like what I've copied over here is going to require an import of matplotlib. So let's go ahead and grab that. So we'll say import matplotlib.pyplot as plt. Okay. So now using NumPy, we're going to set a random seed and we're going to generate data in a range of 200. And we're going to show what the ideal fit would look like, where the data is truly generated from. And then we're going to show the actual data we collected. So this would be collecting data associated with some noise. Let's go ahead and get those values. And in fact, let's clear the console and start over here, just so things are clean. Had some variables left over from the last video. Let's go ahead and import things again. And let's go ahead and generate that data. Now let's go ahead and visualize that data very quickly. So, oh, looks like I missed the actual plotting part. There we go. So, let's go ahead and make this larger. What we see is the example data. So this would be like data you measure in an experiment. And the data comes, this distribution truly lies on this ideal line, but there's all kinds of noise associated with the actual measurement of the data. In an ideal world, we want to be able to generate this same fit. So how would we try to fit a line to this data as efficiently as possible? Well, let's try. What we need to start with is a way of calculating a fit to this data. So I'm gonna make a generic equation name, and you're gonna get a script in your homework that sort of shows how to do all of this. I'm gonna call it def calculate y fit. And you'll put in parameters here, and you'll put in your x data. So in our case, I'm gonna have coefficients a, b, c, and d equal to parameters. Just like in the fsolve video, parameters is going to be an array with the values we want to be able to have our optimizer update to try to minimize the difference between our line and the distance to each point from that line. So I'm going to say this equation, for whatever physical reason I believe, fits my data well. I'm going to say it's a times x data minus b times x data. And let's say we think there's a 3/2 power relationship to coefficient b plus c times the exponential of x data raised to the d. So this is the equation that I believe governs the distribution from which my data was collected. And so let's go ahead and see if we can't find the correct coefficients to fit a line to that data and see how close it is to the ideal from which the data was actually drawn. So go ahead with our equation, we'll go ahead and return y. So this, if given the correct coefficients, will return values of y. They look very similar to the data I collected. But now we need an objective. This is the equation we're going to try to minimize when we update these parameters, because we don't want to minimize the output of our equation. We don't want our values just going to 0. We want the difference between our line and the points next to it to go down to 0, or as close as possible. So def objective, this is again what we want to minimize. We'll go ahead and we'll give it the parameters which we want to minimize. We'll give it the x data, and we'll give it the y data. So from the x data, we can generate our fit, and from the y data, we can check how good we are, how close our fit actually is. So first, let's say our y fit is equal to, well, calculate y fit at the location x data for the current parameters. The next thing we can say is our objective currently is going to be equal to 0, meaning we don't know how much error is associated with our current parameters relative to the actual points. We're going to say it starts at 0, and as we look at each each point, each y data, we'll see how close it is to our y fit, and we'll update this objective. So it's essentially accumulating error. And then our minimizer will update these parameters to drive that error as low as possible. So we're going to say we can say our y fit, let's just go ahead and make sure it's a numpy array. We're going to say it's a numpy array. And we're going to say our y data is also a numpy array. Now this is just to be safe, in case their input is lists or tuples or some other way that doesn't play nice with numpy operations. Now we can finally say our mean squared error, meaning the error associated with our fit compared to the actual data points, is equal to y fit. Now this is a mean squared error, so we're going to get the error, y data, that is the difference between our fit and our actual data point. We will square it, and then we'll take the mean, hence the mean squared error. And then, depending on your preference, we can solve for the root mean squared error, which is the square root of the mean squared error. So what is this stuff? Well, as we go through, we can now say instead of our objective being 0, and updating that objective with each new point we see, we can say, well, let's consider all of y fit versus all of y data, and for each instance in these arrays, let's take the difference. You're familiar with that. And then, once we have that difference, let's square each of those values. Again, you're familiar with that. And finally, we'll take the mean. Pretty simple and upfront. So what is our objective function going to return? Well, remember we want to minimize the error. So we're going to be minimizing something. We're going to be minimizing this objective function. And so we will return the error, be it mean squared error or root mean squared error. I'll go ahead and return the mean squared error. So then our last step is to get a guess. So I'll say x guess, or maybe we'll say parameter guess, is equal to a numpy array, and let's just throw values in there. We'll say 50, 20, 20, and 0. Again, you might have to update this guess in case you start your solver in a bad location. And then we can say our solution is going to be, when we minimize the function, well, the function is our objective. The x0 values is our parameter guess. Let's go ahead and call this x0, just to make things very simple. And then there was a couple more arguments we could put in. Well, the args. In our case, there was 2 args, extra arguments we give to our objective, that is the x data and the y data. Let's go ahead and say args equals x data and y data. And remember, args has to be a tuple, so we'll wrap it in a tuple. And then finally, with this technique, we can choose to include a method. Over here we see method. Now there's different ways in which we can try to minimize this. I'm going to say generally a good one is Nelder-Mead or Powell. Those, I have no reason for saying that besides having success with them historically. So I'm going to go ahead and say my method. Now it'll choose a method by default, so don't feel obligated to put this in, but I'll say it's Nelder Mead. Let's go ahead and spell that right. And I'm going to close up those parentheses, and I'll be minimizing the objective function given an initial guess of 50, 20, 20, 0 for these parameter values a, b, c, d, using as extra arguments to my function my x data and my y data. And with the method Nelder Mead, I'll be minimizing things. Now, there's one more thing we can do for convenience. We can check where our error started and where it ends. So we know that, well, our initial mean squared error objective is going to be our objective function with our initial guess with our x data and our y data. Then once we have a solution, we can update that. Instead of our final SSE object or our final MSE objective being at x naught, it'll be at our solution value for x. So our final MSE objective, well, let's go ahead and before we quite get there, run what we have. Make sure everything works. So we've defined these functions effectively, and we have defined our value x naught. So let's first minimize. Okay, positional argument follows keyword argument. So method equals, so I put in fun for function equals objective, so that's a keyword argument, but then I used a positional argument for x naught. So I can either say x naught equals x naught, like you see up here, or I can get rid of the keyword arguments, since these also work as positional arguments. Let's try this way for now. And so we got a second error. Minimize got an unexpected keyword error arg, and that's because this, I believe, is actually args. We can go to help and we can quickly check. So this is fsolve. Let's get the help function for minimize. And we see here it's args, args. And let's try run it one more time. Okay, so now we have runtime warning, divide by 0 encountered in power. So now we have a warning that something about this function itself is not accepted. So let's go back and see if we can find what type of error may have occurred. So if we go into this function, I proposed a fit where we said we have a times our x data plus b times our x data to the 1.5. So here, if x data is negative, we're going to have an issue because the negative value raised to the 1.5 will give us an imaginary number. And then plus c times np exponent x data raised to the d. Okay, so we have to make sure that whatever we do, values in x data are positive. So let's go ahead and look at x data. Okay, so that shouldn't be a problem. X data is always going to have positive values. So the next thing we can look at is see if there's an issue with our objective function. So we're calculating our fit. Oh, parameters is not defined. We can go ahead and say, let's pretend we know our parameters for now. Say they're equal to this array. So we can get a fit. This would be with our initial guess, how our x fit goes. And you can expect that's probably pretty bad. Convert it to array. We get our y data as an array. So that's very different than the fit when we use these this initial guess for our parameters. And let's see y fit minus y data squared. So we're off by about a factor of 1e to the 9. We get the mean. This should be a positive value. So let's see if we update our initial guess, if we can get something better here. Overflow encountered in exponent. So the value of 10 because it's x data raised to the d, so something raised to the 10 is far too big. So put this at a very small number. And we'll see again. So it looks like we fixed our initial issues by changing our guess value. And so what happened is our optimizer was unable to find a solution, or it was encountering mathematical issues when looking for a solution due to the shape or the topography of our equation. Okay, so if we go to our variable explorer, what does our solution look like? It says our solution is type optimize.optimize.optimize results. So maybe not what you were expecting, but if we open it up, we'll find this little guy here, x. So the rest of this essentially tells us how we did. Our function is successfully converged, and I believe what it's saying is our mean squared error was 1682. So that's the goodness of fit, and these are the coefficients that gave us our converged solution, so our minimization. Now, without any better way of looking at things, we started at, what is this number? Almost 500 million for our mean squared error. And we ended at solution x being the coefficient or the parameters we want. So we ended at, go ahead and call this parameters fit. Well, our objective with our fit parameters, our parameters fit, a mean squared error of 1600. So we've definitely reduced the error associated with our fit. But as a final step, let's go ahead and plot it. So this should be pretty easy because we already have a lot of these functions. The first thing we're going to do is let's go ahead and make a figure. And we'll go ahead and set a fig size equal to 6 by 6. And then we'll do plt.plot our x data against our y data. So this is the actual data. And we'll make it red, and let's go ahead and make it a star. Let's have some fun. And we'll label this as our example data. Now the next thing we're going to plot is our best fit line. So this is going to be x data. And then I want this value to be my calculated y fit at x data. Now for simplicity, let's go ahead and bring this out and we'll call this y fit. We'll go ahead and put it in here. And let's make this a black dotted line. And we'll label this best fit. And then without going through too much effort to make our plot look pretty, we could, if we wanted, add some nice tick parameters. We could add some labels, some limits, a legend. But let's stop here and let's just go ahead and let's first fix that. And let's just go ahead and say plt.show. Let's see if we did okay. So we're going to get calculated y fit. We're going to give it our parameters. Let's go ahead and call this fit parameters. And we're going to give it our x data. So let's rename this fit parameters over here. So here is our y fit. Calculated y fit is not defined. Let me go ahead and fix that. Calculate y fit. So our function to calculate y fit is going to take in the parameters and the x data. And let's go ahead and plot that. So now we can see, if I plot this, this is the solution that our solver got. Now we might be able to do better. Maybe if we choose better initial conditions, or maybe if we update our method. So let's spend a second, not too long, just playing around, seeing what we can get. So that changed maybe a little bit. Maybe a little bit there. No change there. If we up this to 100, no change there. Let's try, I believe it's Powell. So we got something here. Pretty big change. And you can see as we go through, possible that this equation doesn't fit our data, and we can either update our equation or continue to try different guesses in our fit with hopes, if we expect that our equation works, that we get a correct fit to the data. So I'm going to go ahead and try maybe a 60. I'll try a couple more, and then I'm going to update the equation if this isn't going to work, because I actually don't know what this equation even looks like. But when I see that data, I see an x cubed behavior. So let's go ahead and update that to x cubed, and let's give it another go. Well, in this case, I'd go back to the drawing board and I'd rethink, was this the correct equation for calculated y-fit? If it's an incorrect equation, what I can always do is change the equation in here. Maybe I just want it to be a plus b times x data cubed. And I can even get rid of that exponent part. And then for a, b, c, and d, well, I wouldn't need those parameters anymore, so I wouldn't need these two guesses. And I believe it should be able to, with that change, kind of go back through the same optimization process and see where we end up. Anyways, you'll find this type of problem on your homework. Good luck. And if you encounter problems, go ahead and let me know. We might be able to work through them together. Or it might be the case that you simply need to try either better guesses, a different solver, or getting the correct equation that actually describes your data. Good luck.